All right. Good morning, everyone. Let's get started. So I did upload a new partial script on GitHub. I don't remember now if the last time that you did download things from GitHub, if it was already there or not. You can check on your 2024 PSA main folder. The name of the code is 0329 management zone partial. Maybe you already have that from last time you downloaded, and if not, then please just go ahead and download again. And once you do that, I do want to ask you to create a new folder called 11 Management Zone. And then the subfolder is code data and output, and you can move this script into the code folder. So this is right now, this is how my course folder looks like. So the next project, which is the one we're going to be start working today, is the 11 management zone. So that's the one I'm asking you to create and bring in the partial script for that exercise. Well, and I guess I didn't mention, but so also after you do that, make sure you also create the RStudio project for this new exercise as well. All right, I'm gonna get started here. If you still need a moment, let me know. If I don't hear anything, I'm gonna keep moving. So once you have created the project, move the script into the code folder, go ahead and launch that RStudio project. So we see on the top right, the name of the project. We know we're in the right place. And if you're not seeing the script yet, files, our blue button, code, and then just open that. All right. So in this next script here, we're gonna basically create management zones based on the soil and terrain layers that we have, right? So for terrain layers, we brought in elevation as our primary layer, and then we calculated slope aspect and flow direction, even though here we left, I think well, I don't remember now if we already did that, but at some point, we're not gonna use flow direction for the management zone. And then on the soil side, we have electroconductivity at 2 depths, right? So on the previous exercise, we brought all those layers, we merged them, and we validated the spatial temporal stability classes, which were created solely based on yield. Now, our goal is going to be to bring those layers again, but now they have already been merged, so we can just bring the merged version of them, and then use a unsupervised classification algorithm to create zones. And these zones are going to be based on soil. So they're not going to consider yield at all. It's just going to be soil and terrain variables. And then we'll validate them with the actual yield data at the end. So today, again, our goal here is going to be doing clustering. We're going to use k-means as our algorithm of choice. And we're going to talk a little bit about that in more detail. and then assess how these variables are impacting the different zones as well. There are maybe a few packages that I'm not sure we already use in this class. Perhaps you have them for different reasons, but if you don't have these packages, I left you there the install.packages for them. They are FactoExtra, NBClust, and ggpubr. So as always, I recommend that if you don't have them and you're going to install them, just uncomment the first line, just run that one, wait for it to go through, comment it off, and do the same for all three. So you can install them. And after you install them, we just want to run, or after you install them and you comment them off, we want to run the whole chunk. So we load all those packages that we're going to be using.
Excuse me. Can you tell me which QMD is this? Because I thought I bought it the right one, but I forgot. I think I bought the wrong one. Can you tell me the name of this?
The name of the script?
Yeah.
Yeah, so this is 0329 management zone partial.
It is in the management zone. Okay, I found it. Okay, thank you.
Yeah. All right. I'm gonna give just a moment here for you to install those packages. And I guess just a little bit of background. So FactoExtra is gonna help us to understand the best number of classes, and that's gonna, can think about it as the best number of management zones that we're gonna have. NBClust is also going to help us to identify what is the best number of clusters or management zones. And then ggpubr is just to add some p-values on our ggplots that we're going to do at the end of this exercise. All right, I'm going to keep moving here. If anyone needs more time or run into issues, as always, feel free to speak up. And if I don't hear anything, I'll just assume that you're good. All right, I'm gonna make sure to run this chunk here, so I load all those packages. The first thing one of the first things is to bring in the data we're gonna be using. So this is gonna be the data that we exported on the previous exercise. So it should be on the data folder of that project. So let's go ahead and that was a GeoJSON file. So we're gonna use read_sf to bring that in. So we need to navigate to that project, right? So .. we get outside of this code folder, but now I need to get outside of this project. So another .. Now you should be seeing all of your projects. You want to go to that 10 stability validation. That's where the version that we exported last time is. And we want to go into the data folder, which is where we exported that allv.geojson. So if you just hit tab, you should find that, as long as you are able to successfully export this. So if we go ahead and run it and just print it, just to quickly assess it, we've seen this before. So in my side, I have 4,046 rows. In your side again, that may be a little bit different, but it should not be like double it. If it's double or half, then you probably have something going on your side that we need to fix. But it should be around this number, give or take. And then the data we have here is the standardized yield for 17, 19, 20, the mean pixel, the standard deviation, the coefficient of variation, the ST class, and then all the field data as far as terrain and electroconductivity as well. Next thing I want to bring is our boundary, so we can make some plots or some maps and show the boundary. So let's go ahead and call another read_sf. The boundary is in our 05 digitizing project. So open and close quotation marks, .. another .. then we go to 05 digitizing, This is in the output folder, so we can go on output and then bring in the boundary.geojson. Bring that and you print it. It should only have one feature since it's just one boundary. In this case, it is WGS84. And just to remind you here, all V is actually already in UTM. So let's go ahead and just for consistency's sake, just transform the CRS of our boundary W. So you can notice, and this was a question in the exam, it already has a CRS, right? So we don't need to set, we just need to transform to a different one. So let's go ahead and give it a pipe right there on that after the readsf, and just use the function st_transform and give the CRS equals to 6345. So now if you print it, it should say here on the bottom that's a projected CRS, the same one as we have on the first layer. All right, and then just a very quick EDA here asking for a summary. We've seen these variables before, we plotted them before, so I'm not going to do a very extensive EDA at this point because we have already done it. But yeah, so we see here that the numbers are what we were expecting. So the standardized yield ranging there from 24 to 156 in 2017, from 6% to 178% in 2019, 33% to 154 in 2020. The mean of the pixels ranging from 41% to 135, coefficient variation from 0 to 75%. And then just our field variables that we've seen before. We have these NAs here. I hope you remember what they are. Already talked about them a few times, why we have some NAs in some columns and not in others. So let's get to our k-means exercise. So before we actually go ahead and perform k-means, I do want to talk about some of the theory so you understand what is going on. So k-means it's an unsupervised clustering algorithm that's going to partition the data into k number of groups, where k is going to be defined by you. So we are going to tell the algorithm, this is how many k's I want. These are how many groups I want to get out of this algorithm. So let me print here an image so we can talk about it. So imagine that here we have two variables, whatever they are, dimension 1, dimension 2. They could be, perhaps soil VCA and elevation, or any other variable that we want to plot here, right? So if we look at this plot, and if you had to guess how many groups there is in this case here, how many do you think there are? 3, right? It looks like we have 3 distinct groups, one being this one being this one being this one. So it's always good to have some sense of how many groups to expect, because then you can provide the number to the algorithm and say, hey, calculate and run k-means on this data set, and I think there are 3 groups, so ask it to give you 3 groups back. However, it's not always easy to visually assess it. Imagine that the more variables you have on this clustering exercise, the more difficult it becomes for you to visually see that. Because in this case here that I just showed you, we have 2 dimensions, right? X and Y. Now imagine that you give your algorithm 100 variables. How can you visualize that so you get an informed decision on the number of clusters? It becomes impossible. And so, if we think about our example here, if we come back to a simpler example, just understand what k-means is doing, we're going to show how k-means would behave for this example here, which is not our data set, it's just an example data set. And the way that, so if we tell the algorithm that we think there are 3 clusters here, go ahead and look for 3 clusters. The way k-means works is that the first step, k-means is going to randomly pick 3 starting points on your data set. And 3 because we're telling we want 3 clusters. So we randomly pick 3 centers. Let me actually show you here this So the first step that K-means does is it randomly picks 3 actual data points from your data and assign them as the cluster centers, right? So we see here in the first step of this example, it randomly chose that point, and this point. It calculates all the distances from all points. Everything you're seeing here is getting a distance calculated from that point to the center of all of the other clusters or cluster centers like we're seeing here. And then whichever cluster center a point is closest to, that point's going to be assigned to be a member of that cluster. So for example, we see that all the points that are colored in red, they're in red because they're closest to the red center rather than any of the other ones. All the points that are purple, they're purple because they are closest in distance from or to, they're closest to the purple center here, and all the green ones are closest to that green center. And again, these 3 points, these 3 centers here were just randomly selected variables from your data set. And so what happens here is that the first step again is randomly assign or randomly select 3 rows from our data set and set them as the centers. Then each one of the data points is assigned to be a member of one of those centers based on distance. And at that point, the center then recalculates the cluster mean. So now that it has all these red points associated with this center, it uses all those data points on the X and Y variables and recalculates the center mean of this red cluster. So that's going to move, instead of being here, is going to move somewhere here. And at the same way, for the purple was going to move somewhere here. For the green, it's going to move somewhere here. So it's going to just find a new center, which now does not need to be a variable anymore. It can fall anywhere in the space of the data. Does not have to be an actual observation. Sorry, that's what I meant. It does not have to be a new observation. It's just going to be anywhere in the space of the data. And so the algorithm pretty much keeps doing this. So it finds the centers, calculates all the distances, assigns a membership, looking at all the points that were assigned a membership of a given group. It recalculates the center of that cluster. So the center moves there. It recalculates all distances of all the points, reassigns membership until that center of the 3 clusters start moving around, and at some point it's going to stabilize. It's not going to change anymore. And that's when K-means reaches convergence. So that's when you finally get your final membership of the points. So I want to show you here a GIF that shows us how that works. So we have multiple steps. Let me see if I can. Yeah, okay. So if you look at the title of this, it starts at step 0 and goes through, let's see, 12 steps. You can see how the crosses are changing until they stabilize to actually find all 3 clusters. So this is what's happening iteratively with a K-means algorithm. First, randomly chooses 3 observations in your data set, assigns them as the cluster centers, calculate distances from all points to them, assigns a membership to the points, recalculates the center mean, and then keeps doing that until it converges. So you can see, this is just in a loop, right? But starts, so the X's start right there, and then they start moving until they don't move anymore, and then K-means ends its process. So this is important and it's useful because a lot of times we don't know how many groups we have, right? So that is the goal of a unsupervised algorithm, is when you do not have the answer of how many groups you have there, right? It's different from our ST class, for example. So the ST class, they were created, the unstable, high stable, medium stable, low stable. Those classes already, we created them out of the data. So we had that column, we had that label, right? We knew where they were in space. In case of this, in this case here, we do not know where our management zones are. We're gonna allow the data to tell the algorithm and to work together to give us that answer of where are our clusters, which in this case, they are management zones. All right, so talking a little bit about k-means here. So as we just saw, k-means is used for clustering, or in our case, more specifically, we're referring to clustering as management zone creation. It is an unsupervised analysis. So what do we mean by that? So unsupervised is when, if you think of a formula y explained by x, unsupervised does not have a y. It only has variables on the x side of the formula, right? So we do not have a predicted variable. We do not have a response variable. We just have predictor variables or explanatory variables that go on the x side. So we're not telling it, here's what the classes are, try to explain them to me. We're saying, here's a whole bunch of variables, group them in a way that makes sense for me. So again, it only takes predictors, which are the x variables on this formula here. And these predictors have to be numerical, at least for k-means. In k-means, all of our predictor variables need to be numerical. So in this case here, even though flow direction was like, it gave us a number, but we know that number did actually not mean anything. It was just a class, right? It was just, I guess one was east and whatever, all the matrix that we already looked into. So those are basically not really numbers. They're just classes. So we're gonna have to drop flow there for k-means here. So k-means, the reason why I'm showing you k-means is I think this is probably one of the most popular and common unsupervised algorithms in statistics. And there's a lot of use of that in agriculture for different reasons. So another one that maybe some of you here are gonna run into that you can use k-means is, so let's say if you have a drone imagery and you want to remove soil pixels, right? You can give your sensor data, so your bands, your VI, vegetation indices, to k-means and ask it to create 3 groups. And then it's going to create 3 groups, and then it can look at those groups and say, well, I see here that group number 1 is mostly plant pixels, group number 2 and 3 are soil and maybe shadow, maybe something else. So you can basically remove the pixels that belong to the groups that are not plants and only keep the plant pixels. So then it can take averages for a plots without allowing the soil and shadow pixels to interfere with your average of the plots. So that's another application that we may have, especially with imagery. So anytime that you have things that you want to create groups, and you may not know where those groups are, k-means is one of the algorithms we can use as an unsupervised algorithm. So even though k-means is very useful and very popular, it has shortcomings as every analysis. So I want to show you some examples here that k-means is going to be the most useful when your clusters are circular. So they have a circular shape and not necessarily in a spatial context. Because really, as you're going to see here, we are going to create management zones without regard for spatial coordinates, where the cluster does not know that a pixel is neighboring another one. It just sees these data just as rows in a data frame. It has no information on the geospatial component of it. However, when our clusters are not circular, so if they have odd shapes, or if we have outliers, so if we have like a very circular group that you can see on the plot, but then you have many outliers, k-means can fail miserably. And I just want to show you here some comparisons of different algorithms and different data sets and how clustering performance was compared. So this is a figure from a paper where each column here is a different clustering algorithm, is a different unsupervised algorithm. Each row is a different data set. So these data sets are just 2-dimensional, X and Y, but they created them just fake data sets with different shapes and to see how different algorithms would perform. So k-means is the first one here. The first column is k-means. Perhaps some others that you may come across is spectral clustering, agglomerative clustering, dbScan is also a very popular one, and Gaussian mixture as well. The other ones, I don't think I've seen them too commonly in ag, but anyways, these are all different clusters. So what I want to show you here is let's look at k-means first, which is the first column here. So in the first data set, we see that we have two circular clusters, right? But what k-means is doing is basically cutting right through them and splitting in the wrong way, right? You should really call the inner circle here one cluster, the outer circle another one. And k-means does not handle that. For example, spectral clustering did a good job there, and others as well. But k-means did not. This other shape here as well, k-means did not do a good job. So it's basically cutting right through two of those clusters, whereas they should be clustered like this, right? This would be the correct membership. When we look at the third case, which is where we have more circular clusters, k-means does a good job. And I think every algorithm here is doing a good job on that data set. When we have these elongated clusters, so non-circular, more ellipsoid types of clusters, k-means is also not doing a good job. Perhaps here spectral clustering is doing an okay job, dbScan as well. When we have very circular and well-separated clusters, k-means is doing a good job. I think every algorithm is doing a good job. And then the last one here, I'm not sure what would be the correct answer, because it seems like to be just like a square that, algorithms are just trying to create clusters of. So as you can see, k-means is very simple, it's very powerful, but it has shortcomings, and I just wanted you to be aware of those. Okay, so up until this point, we've only looked at examples here on this script where we had just two dimensions, right? So we had X and Y, and we're just seeing the performance of, in this case, k-means and others as well. But if you have many variables, like in our case, I think we have 6 or 7 variables, it's going to be difficult for us to make a plot like this and really make sense of what's going on. So we can properly choose the number of k, right? Because again, number of k is going to be a variable that we determine. We're going to tell the algorithm, this is how many k's I want to have. So, if you heard of this before, the curse of the dimensionality is we start having so many dimensions, so many columns in a data set that we're given this algorithm that starts to become difficult for us, for humans, to really be able to plot and make sense of all these variables at once. So we can use some machine learning techniques here, like data splitting, doing training, validation, and so on, which is beyond the scope of this class. We're going to be seeing this in my other class this semester. So for this class, we're skipping that. But there are other ways that we can actually, in the case of k-means, there are other more straightforward ways that we can use to determine what is the number of k that we should use in a given situation. So, okay, this part of the script, we're actually going to start working with our data. So before we can run the k-means algorithm, we have to do a little bit of cleaning on it or getting it ready to be run for this algorithm. So a few things that we want to do here is, so k-means does not handle NA values. So we're going to have to drop NA values first. So even if you have, if you have a data set, in my case, with 4,046 rows, if I have one NA value in any one of those columns, that's already not going to work for k-means. So we have to remove NAs first. We need to keep only numerical columns. As we said before, k-means only handles numerical variables. It does not handle categorical variables. So we're going to have to drop those. And then we want to standardize these variables. What I mean by that is basically using some type of standardizing procedure, which could be, for example, standardizing around, so in a way that all variables have a mean of 0 and standard deviation around that mean. And this is basically so we do not let variables that have a higher magnitude to be more impactful on the algorithm than variables that have a lower magnitude. So one example here would be, we have the slope, which is ranging in numbers, numerically is ranging from 0 to 7, and that's in percent. Whereas if we let aspect play a role, aspect is ranging from 0 to 360, which is in degrees. So that variability there of just the numbers, the magnitude of the numbers, we don't want to allow for that to impact the algorithm, because variables that have a higher magnitude will probably have a higher weight on the algorithm, and we do not want to let that happen because it's just a nature of the variable. It's not necessarily that aspect is more important than slope. So I just left you here a chunk for a summary, just so we can run again and see those variables. So we have a lot of numerical variables. Really for us, for our goal here, we're going to use elevation, slope, aspect, flow direction is going to be left out, and then ECA, shallow and deep. So those are the variables we want to keep. And even these variables that we're keeping, we have some NAs, so we're going to have to drop those NAs as well, and then standardize them afterwards. So if you come here on the next chunk, this is where we're going to do all that processing before actually running k-means. So if we start there, I'm going to call that object all vn, and this n here is just to mean that these are the numerical variables. So if we give it a tilde, let's start coding here. We're going to start off with all v, which is the object we just have above. Let's go ahead and add a pipe. So the first thing I want to do here is to drop NA cells. There's probably a handful of ways that we can do this in R. I don't remember if we've done this in this class, but I guess either way, anyone here has a guess of which function we can use to drop NAs? Can you say that again? Okay, so we have that argument that was na.rm, right? So we use this argument here inside of like mean and standard deviation, mean max. But this is an argument, so it would not be well, maybe there is a function, but I don't think it is a function. Any other thoughts here of another function we've used in the past to just drop NAs? Yes, so there's a function called drop_NA coming from tidyr. If we just leave it like that, it's going to drop any. So if a row in our data set, my data set has 4046. If a row has at least one NA in one of the cells, it's going to drop all those, the whole row, right? So it's going to take the whole, even if I have like, let's say I have 10 columns, and then for that row, I have values in 9 of those columns, but I have one column that I have an A, it's just going to drop the whole column, right? So that's what drop NA does. So in my case here, if I just check all V, I'm starting off with 4046. If I run this now and I print all VN, now I have 3723. So that's, just dropped, I don't know, maybe about 300 rows that had at least one NA in that row across different columns. All right, so the next thing here is let's just select the variables that we want to have in this exercise. So let's add a pipe. For select, we're going to use the function select. I always like to use the dplyr : select. When I was preparing one of these exercises here, I noticed I forgot to do that, and it was a script where that made a difference. So I was getting an error. I was not sure what was going on, and sure, it was because I was not explicitly calling select from dplyr. So if I just print here all V for us to look again, we want to keep the variables starting on elevation and ending on ECA 90 DSM, except for flow dir. So and I guess we're also leaving aspect out. So what we're going to do here is just starting on elev_m, we give it a colon, and ending on ECA 90_DSM. So we're selecting all those variables in between elevation and ECA 90. However, there are 2 in there that I want to remove, which are flow direction. So I want to do a minus flow dir, give it a comma, and a minus aspect. So we're also leaving aspect out. So if you run this and you print all VN, so we notice that the drop NA had an effect on the number of rows, and now the select had an effect on the columns, right? So now we have, in my side at least, I have 3,723 rows and 5 columns, where those columns are really the ones that I want for clustering.
When it drops, does it drop that many cells? Like whichever one has the most NAs, does it drop that many for all of them?
So,
Or
so,
the same number?
so the drop in A, so let's say that we have, if you just think of a simpler data set where we have maybe, let's think about like 10 rows and 10 columns, right? So drop in A is working at the row level. So it's going to look at the first row and it's going to look across all the columns. If you have at least one NA in any of those columns, that whole row is going to be dropped. So it's not on a cell by cell basis, but on a row by row basis, right? So it's just leaving in the data set or rows that have values for all the columns. All right, so next step here is I want to standardize them. So if we just give it a pipe there and come after the comments. So we're gonna use here, I don't remember now if for this class we've seen this before, but because I want to apply a given function, which is gonna be to apply the name of the function is called scale, which is going to center on 0 and have a spread around 0 for all the variables. So it basically takes the mean and then divides by the standard deviation of that column. So I want to apply that function to all the columns here. So we're going to use this function across, which we've seen in the other class. I think we may have used that in this class as well. But we start off with a mutate. And then inside of this mutate, we're going to call this function across. So the way that this function works is I want to give it a condition X, and then I want to say, well, what function I want to apply for the columns that match that condition, and that function is going to be on the Y side. So first thing, we want to specify which columns I want to standardize. If you look in our data set, all columns are numerical except geometry, right? Geometry here is not a numerical column. So basically, we could tell this in a couple of different ways, but the way that I want to show you here, which perhaps is going to be something you can use for other cases, is I want to use a function that is called, okay, let me think about how can I make this less confusing. So I want to use a function that is called where first. So I'm going to say where this thing is true and where it applies to the columns. And this thing is the function called isNumeric. So it's a little bit of a nesting of functions here, which I normally try to avoid, but in this case, is probably what we want here. And then the isNumeric, the way that this function works is we do not need the parentheses. So here's how that will look like. So I'm saying across all columns where those columns are numeric. So here I'm basically selecting only the numeric columns. And then we give a function. So here on the Y side is where we give a function. We give the tilde first, and the name of the function is scale. And then I need to say .x, so it understands the scale. .x here is a placeholder for all the columns where they match the condition of being numeric. So I know this looks confusing, and it is confusing, but this is how you would automate this process for all columns that are numeric. You basically apply the function scale to them. So if you run this and then you print it, if you got all of the, if you open and close your parentheses on the right place and you have the columns correctly, it should have worked, and then you should see something like this, where now all of our variables, they have a mean of 0 and then a standard deviation that depended on the standard deviation of that column, but they've been standardized and normalized in a way that now, a variable that had a larger magnitude is not going to impact more than one that had a lower magnitude in this data set. Okay, so this is basically the processing we needed to do in this data set. Now let's do our management zones. So if you come to the next chunk here,
I'm unable to do that. There is an error coming.
what is it telling?
It is the same line that you are told that is complicated. Error in across where is numeric. There is no further information. It's just that there is an error.
Okay, so what I would check is, so we have here across opening parentheses and then where opening parentheses and then is numeric, we remove the opening and closing parentheses of that. So if you have
Yeah,
open
I did
closing
that.
parentheses of is numeric, just make sure you delete that. But then you do want to close your parentheses for the where right here. So right after numeric, you have a closing parentheses that is closing the
I
where.
did that. There is one more line in the console section. Must only be used inside data masking verbs like mutate parenthesis, filter parenthesis, and group by parenthesis.
Did you have the pipe here?
No.
Yeah, that's probably it.
Yeah. Yeah, it was pipe.
So is it working now?
Now it's working. Yeah.
Okay, awesome.
Thank you.
Yeah. All right, so, we're gonna need to define how many management zones we have here, but to start off, maybe let's just play a little bit with it and let's ask it to give us 4. Okay, so if you come on this next chunk, here's where we're gonna do k-means, so just give it the assignment symbol. The name of the function is k-means coming from the stats package. The first thing we give here is a data set name, which is the one that we just wrangled above. So that's all underscore v underscore n. However, if we print that data set, it is an SF object, which means that it has a geometry column, which k-means does not handle. I did not want to remove the geometry column at this stage of creating all VN because we will need that to plot the results of the clustering algorithm. So what we're gonna do here is do a change on the fly, which is not going to affect the object all-vn, but it's gonna affect the data set coming in k-means. So if you come here after the all-vn, give it a pipe, and let's just call the function st underscore drop underscore geometry. If you just run that all v pipe and then this function, it becomes a tibble that it has the same number of rows, same number of columns, but now it does not have a geometry anymore. So again, this change we're doing on the fly. We're not truly removing the geometry from the object OVN, which we created on the chunk above. We're just doing on the fly here. So we give k-means a data set that does not have a geometry. And then there are a couple of arguments here. So if you give a comma after the drop geometry and break code a few times just to read better, there are a couple of arguments that we want to change. So the first one then is called centers. So centers is really the number of k, the number of centers that you want k-means to find for you. Let's start off with 4. And then the next one is called nstart. So nstart is how many times you want k-means to run to give you like an average result of the center of the clusters. As you saw on the first step of k-means, it randomly chooses. So for a k of 4, for centers equal 4, is going to randomly choose 4 points in our data set, and those are going to be the starting points of the algorithm. Because sometimes, depending on your data complexity, how many rows you have, how many columns you have, that randomness of choosing where to start on the first step can give you different results in the end. So to avoid that from happening, we ask it to run itself more than once and give you the average results. So that's what nstart is. So I want to say nstart equals to 10, meaning that k-means is going to run 10 times with 10 different random selections of the first step and give you the average result at the end. This helps us to avoid, running once and maybe getting results that are impacted by the random selection of the first step. Okay, so if you go ahead and run this, it should have run correctly. And then if you print this object, it has a whole bunch of things here. So one of them is giving you what is for each one of these variables is going to give you the average of each one of the clusters for each one of the columns. So basically here, each column is one of the variables that we use for clustering. Each row is one of the centers that we asked or each one of the case. And it's giving you for each one of them, what is the average value for those clusters. So if you were to make a plot in 4 dimensions, that point right there, it was all these points here would be where cluster 1 sits in this space. And then it uses that algorithm to give you a membership of all of your data points. So this is the actual, these are just like for each one of your observations, this is the membership of each one of those classes for them. And it's just a very long print because it's like 4,000 rows. So we can just, I guess we actually have to get to the bottom of this because I want to show you something else. So this is one of the metrics that we get out of k-means, the within cluster sum of squares by cluster. So what this is giving us is just so there's a total sum of squares, which is the variability of the whole data set, and we're dividing the between clusters sum of squares. What does that mean? You can think of this as the higher this ratio here, the more variability you are explaining with the number of clusters that you ran. So in this case here, we have 4 clusters. Having 4 clusters, I was able to explain about 61% of the variability of this data set. Now, we just kind of like randomly, I guess, chose 4 clusters. You know what? I think this is probably a good stopping point for us. I don't want to rush things. So maybe let's just stop here. And next class, we start here where we ran k-means with 4 clusters, or in other words, 4 management zones. And we were able to explain 61% of the variability of this data set. Next class, we're going to pick up from here, where we're going to change the number of k to be higher and also lower than 4 and see how that impacts this number here. And then we're going to get into making a objective decision on what is the best number of k's for us to use in this case. All right, any questions or issues until this point? And very likely on your side, you have a slightly different number here because of, again, all the way going back to the boundary being different for all of us, which means the grid was slightly different and therefore interpolation was different and so on. But you probably still have a similar value somewhat to this one. All right, so make sure you save your script. Let me go ahead and open an issue for attendance.
Hey, Dr. Bastos, question, do you still want to meet with me and sometime afterwards?
Yeah, so is that Clint?
Yes, sir.
Yeah, so Clint and I think, so Rolando, let's see if Rolando is in the call. Yep. So if you guys want to meet, we can meet right now. I'll go back to my office and then we can meet there. Let's see, maybe if Clint, could you create a Zoom link and then send that by email to both Rolando and I?
Yes, sir.
Okay, thank you. And then we can connect on that.
All right.
Let me come here and open an attendance issue. All right, I just opened an issue. Make sure to claim your attendance. Yeah, and Rolando just shared in the chat his email. I don't know if you can see Clint, but it's jrolando@UGA. Awesome.
I got it.
All right. Okay, well, after claiming your attendance, we're good for today. See you Wednesday, and I see Clint and Rolando in a moment here. Thanks, guys.